So this is our fourth lesson on integration, and we're going to look at evaluating something called a definite integral. And before we do that, I'd just like to ask you a few questions and recap what we did last lesson. So if you want to pause the video and work through these examples, I'll just put them all on the screen at once, and then I'll go through the answers. So let's start with the first one. So we're going to add 1 to the power, so it's x to the 6, divide by the new power, add on our constant of integration, and simplify that where possible. We're going to take each term and integrate it in turn, so x cubed, add 1 to the power, divide by the new power, I'll put the 2 back, plus integral of x, because there's a 1 there, and that becomes x squared, divide by the new power, I'll put the 4 back, plus c, and again we can simplify this one, so that should be 2 there, and that'll be 2 there. Moving on, when we integrate a constant term, that just gives us x. Again, when we integrate x, because there's a 1 there, we add 1 to the power, so it becomes x squared over 2, and I've got to take 2, and then integrating x squared, I get x cubed over 3, take 3, and I've got plus c there, and again I can simplify those fractions because the 2's and the 3's cancel. It becomes slightly more tricky when we have fractional indices, so when I integrate this I get x to the 3 over 2, and I have to divide by the new power 3 over 2 plus c, and dividing by 3 over 2 is the same as timesing by 2/3, so this becomes 2/3 x to the 3 over 2 plus c. And this last one, I need to write it in standard index form first, so this would be x to the negative 2 over 3. So when I integrate that, I get x to the 3rd, divide by the new power, which is a 3rd, plus c, and dividing by a 3rd is the same as timesing by 3, so I get 3x to the 3rd plus c. So we're going to have a look at what we mean by a definite integral. So a definite integral has a specific value, and when we integrate this term, the expression that we get, that we're going to call I of x, we then evaluate it between two values of x, which we write at the top and the bottom of our integral sign. And when we've got our integrated expression, we enclose that in square brackets and put these limits of integration on the right hand side. And because in each term, when we evaluate it first with b and then with a, we'd have a plus c, the subtraction, the constant term would disappear, and so there's no need to put a plus c into our integration. So let's look at an example and see what we mean by that. So let's just focus on integrating 3x squared. So we'd add 1 to the power, divide by the new power, I'll put the 3 back, and rather than putting plus c, we said we don't need to add a constant for a definite integral, and then I'm going to enclose my expression by square brackets and put the limits of integration on each side. Obviously I can simplify that further. We're then going to evaluate this expression with each of the limits. So it's this one on the top, so it's 2 cubed, take away this one on the bottom, 1 cubed. So that's obviously 8, take 1, which is 7, which is our final answer. And this process here, where we're doing the substitution, is really important, because quite often in exams, although you could do all this on a calculator, if this is wrong, you'll lose marks, and there's often a mark for showing that you've clearly substituted in the limits. So however trivial it seems, it's worth writing that down to make sure you get maximum credit for your work. Let's look at a slightly more tricky example. So this one, before we can integrate, we need to expand the brackets. So I'm going to expand x to the third take 1 times x to the third take 1. So that will give me, let's look at the expanding those brackets just like we would with any quadratic. So this gives me x to the 2/3 take x to the third take another x to the third plus 1. So it simplifies to x to the 2/3 take 2x to the third plus 1. So I can rewrite my integration as this. I'm going to put brackets around all these terms. 2/3 take 2x to the third plus 1, and don't forget the dx on the bottom. So let's change the colour. So integrating each term individually, x to the 2/3, so add 3/3 on becomes x to the 5/3, so I've added 1, divide by the new power. X to the third becomes x to the 4/3, divide by the new power. I put the 2 back, and when I integrate 1 I just get x. I'm going to put that all inside my square brackets and then write my limits of my integration, the values that I'm integrating between on that side. So let's just tidy it up again. So remember, dividing by a fraction is the same as multiplying by the reciprocal, so I get 3/5 x to the 5/3 take away, so this would be 3 times 2 on top, 6/4 x to the 4/3 plus x, and then evaluating that between 0 and 1. And obviously I could simplify that one further to 3/2. Let's change the colour again. So what I'm now going to do is I'm going to evaluate this expression first of all with 1, and then subtract away this expression evaluated with 0. So it reduces to 3/5. So 1 to the power of anything is just 1. Take away 3/2 and plus 1, and then I'm going to take away 0 to the power of anything. It's just 0, take away 0 plus 0, so it's take away nothing. So let's just write this all as tenths. So this is 6/10, take away 15/10 plus 10/10. So obviously that gives us 1/10 as our final answer. So we're now, I think, in a position to have a look at exercise 13D on page 296, and when you've done that you might want to have a look at an application. So an application of integrating our definite integrals is to find the area between a graph and the x-axis, so between a curve and the x-axis. So in this particular example, and we'll look at this next time, the area, let's call that A, the hatched area there, is the integral of this curve between 1 and 4. So next time we'll talk about integrating using definite integrals to find areas between curves and the x-axis.